Um, so it's a pleasure to have Barak Zackay here this week. This is the third talk he's given this week. Here, he's a senior scientist at Weizmann Institute. He did his bachelor's degree at Bar-Ilan University and his PhD at Weizmann. Then he was 5 years at the Institute for Advanced Study in Princeton before joining the faculty back at Weizmann. During his PhD thesis, he revolutionized the way astronomers add and subtract images. So if you have two pictures of the sky and you want to see if something's changed, obviously you should subtract them. But of course, the telescope focus will be a bit different. The orientation will be different. The atmospheric seeing will be different, so the images don't match. And astronomers had been fudging this problem for 40 years. And Barak and his colleagues showed that there was one correct way to do it, and since then, everybody's been doing it his way. In other topics he's worked on are fast dedispersion algorithm for finding pulsars and fast radio bursts in radio observatories around the world. Is much faster than previous methods. Streak detection in astronomical images for finding asteroids and other moving things. New pipeline for the Fermi gamma ray telescope and discovering 50% more short gamma ray bursts. During the talks he gave here were, one, if you have 200 photons over 10 years and you want to find which one of the 10 to the 13 possible spin periods fits those 100 photons in 10 years, you use his method. Does it in a second. And he also talked about new ways of finding transiting planets in Kepler data much more efficiently, and new ways of doing radial velocity measurements with much higher precision than previously, speckle interferometry. And today he'll tell us about the quest to improve gravitational wave detection. He is here still tomorrow. You can try to squeeze yourself onto his schedule. So if you have data and you want to get more out of it much faster, you should talk to Barak. And the motto of his lab is making the impossible a matter of hard work. So today he will tell us about the hard work in gravitational wave detection.
Thank you. Thank you for this intro. Wow, this was very kind. I don't know, is it me? First, I want to thank you for the second opportunity to give a colloquium in Caltech. I don't know why I have this honor. It is great, and visiting Caltech, lesson learned number 5 is that I should do it more, because every time I come here, I have new ideas. So the fast dispersion measure transform was actually a result of a visit to Caltech. So I was a master student, and I came to Greg and asked, okay, just give me a problem you don't know how to solve. And he gave me the right problem, which is priceless. So thank you, and thank you, Shri, for the hosting. And thank all the students for the stimulating talks. In Hebrew, we say, המעז מנצח, or I don't know, the one who dares wins. And it seems Caltech has this spirit. So I want you to appreciate how unique this is. Okay, so the quest to improve gravitational wave detection, parameter inference, and multi-messenger astrophysics without further ado. So Sterl said many things. The heart of them is statistics and algorithms. So let's have some language. So statistics is what to compute. What do I want to compute for my data? That's a question for statistics. It starts with a physical question, okay? And goes to a model, and only then you decide what to compute. And then sometimes it's very hard to compute, so you might want to figure out the way to compute it. And the phase space is so large that there's a whole field called computer science that this is their subject. So first, what to compute. There's a whole field of statistics that will help you do that, and then how to compute it. And it's very useful for me to separate these because sometimes you get into some weird box because you did not. Okay. So the challenge in statistics is very similar to the challenge in physics. You have to make an approximation of nature that is A, close enough to describe reality, and B, solvable mathematically or computable using an algorithm. Okay, those two things are sometimes contradictory. And this is the challenge in statistics, and it's very similar to physics. So as a result, I think most of the statistics that is usable by physicists, you would actually find that physicists were developing it. And it's soft technology, it's easily transferable. So this image subtraction algorithm that Sterl told you, that's a piece of statistic that basically has many implementations now, and I'm not maintaining none of them. And it has been very useful for me to take something that I think has worked in one field, was important, and I will then think about where else this is important, and this had been the best way to expand to other fields. Yes, and you sometimes make a discovery. So previous chapters. I saw in YouTube that it's actually recorded, my previous colloquium, and I would feel embarrassed to give the same colloquium again. So if you want to see the details of that work, okay, this previous chapter, then there's a full recording from this room 5 years ago when I actually remembered something about this pipeline. Okay, so when I was a postdoc, at the moment of weakness, I managed to corner Teja, and we decided to go and see why we could not figure out why this LVT, people who remember, there were 3 detected gravitational waves originally in 01. One of them was not certain. We could not understand why it is not certain. It was SNR squared 100. I made a computation. Should have been certain. And I cornered Teja. And from then on, we are on a journey. It was a very prolific journey. In 02, we managed to double the sample of binary black hole mergers. I wish there was some trick I could tell you, but it's more like a combination of 4 different tricks. Each one of them is boring in its own way. And all of them in statistics. LVK adopted some of our novel methods, and they are implemented, I believe, in PyCBC and maybe also in others. Alex Nitz verified our detection, so he implemented the technology and verified our detection, so you can find them also in other catalogs. And our catalog is now in the community catalog in the GWOSC website. So, and we detected only a few in 03. This is because the technology, the search technology, improves, and we lost our edge. So we either have to come with new novelty or just stop scratching the barrel. So one new novelty that we can do is to search for things that have higher modes. Okay, so higher modes. So if you look, you probably at the home of LIGO, you've probably seen these curves. So those are the amplitude spectral density. Okay, so that's the level of the noise as a function of frequency. Okay, so that's like the interferometer. And then the waveform has some amplitude spectral density. So every waveform has some amplitude as a function of frequency. And it starts at a frequency that is almost 0. And then it goes on for billions of years until at some point it will get into your band. From here on, you have very little cycles. So this is a very heavy merger. So 1, 2 cycle up, it's dead. Okay. And higher modes happen when you are very near the merger. The emission of the gravitational waves is not well described by something that emits a quadrupole pattern on the sky. So there are corrections to this, and those corrections are proportional to V over C to some power. So they are always below this 2, but at some point, because these corrections have a different scaling on the sky, they have a different frequency. So if this thing is twice the orbital frequency, this thing is 3 times the orbital frequency, and this thing is 4 times the orbital frequency. And since you have this wall at low frequency, then suddenly it could be that important for the high masses, specifically for the high masses, it will be important to analyze it with all the modes. So we said, okay, here there's a clear science case. If we want to know what's happening in the high masses, we need to do something about this. And what we could do is to add these modes to the analysis. So J, which was a postdoc at the IIS at the time, and Ajit, which was a postdoc at UCSB at the time, they led this effort, and it was fruitful. The search design is very easy. It's the same as the other searches in some sense. It has an additional thing in which you use all the modes. So you do a mode by mode filtering with the data. And then you some absolute value square this thing, and you get that. And that's a less sensitive search, actually, the way it is framed like this, because you are actually taking things that are unphysical, okay, and you are enumerating them. So the phase of the 2, the phase of the 3, and the phase of the 4, they are not independent. They do change with orientation, but they are not independent. And also the amplitudes are very dependent. So the whole purpose of this thing is just to pass candidates to something that will marginalize the sky position with all the phases and everything. Okay? So you need 2 pieces of technology. 1, to just search with more modes, and 2, to have a very efficient sky marginalization. We figured it out. It works. Yeah, so this is a demonstration of this. So things that are unphysical are this orange. The physical things are these things. You're not seeing the phase here, but the phase itself, among this and this, I think there's only 1 phase that is independent. And if you want to see the noise background, then if you don't do anything, so unconstrained higher modes, you get this. So it's much less sensitive search. So you lost like many points in chi-squared. So that will translate to tens of % of losses in the gravitational wave volume. And then if you do the integration, you have this, and you gain some sensitivity. You also have gained some extra triggers, but it turns out that it compensates. So you can measure the VT. So I must say that from the equations, you know that it has to be more sensitive. And the fact that you measure the VT years later should not surprise you that it is indeed more sensitive. Okay, so it is what it is. It's tens of %, but it's at the highest masses, and we felt it's important. Also, at the highest masses, you need to deal with all the glitches. So we tried, not particularly successful. I would say just as successful as any other search. So what will it require to add more physical effects? So first of all, you have to make a bank. Okay, and that bank is now multidimensional. Every waveform has also the perturbations. So for example, if you have a 2 waveform, it has the higher modes that are perturbations that you need to add some coefficients. But you could also have eccentric harmonics. You could also have precession harmonics. So you have these perturbations. So you make a bank, and you filter mode by mode. And then you do the coincidence. And for every coincidence, you do a marginalization of the full evidence integral. Sounds easy. Not so easy. It's not so easy because if you ask a few years ago, the full evidence integral is a huge pain. It's weeks to compute, and it's not robust. Not robust as in it costs students time, not computer time, students time. Okay, that's and I heard from Alan yesterday that it still takes student time. So maybe we have some motivation to solve the parameter estimation problem. So evidence integral and parameter estimation are I don't know, cousin problems. So parameter estimation of specifically precessing gravitational waves, it was weeks. We want it in seconds. because if it takes weeks, you cannot bring millions of triggers through the process. And we want to do something that is even more heretic. We want to not use a sampler. Okay, so a sampler is a process that has starting position, or maybe 1,000 starting position, and it will do some peak finding process, trying to find the peak of the likelihood. That thing is great. It's great. It's a great piece of technology, but robustness is not guaranteed. You are not guaranteed to find the right solution, and there's a good reason for this. The problem of sampling is NP hard. If you go to the Department of Computer Science, they will tell you, what do you mean a sampler is better or worse? This problem is NP hard. It's better or worse for a particular problem. People are using samplers, and we want no samplers because we want a guaranteed success. Okay? Okay. Is it possible? So first, we had some realization. We realized that we can write the likelihood. So these are the external parameters, and these are the internal parameters. So we can write this likelihood as some sum over modes and whatever of a tensor that has only the intrinsic parameters, a tensor that had only the extrinsic parameters, and those, let's call them the ultra-fast parameters, the distance and the phase, that you can just either analytically or as a grid marginalize them. And why is it useful? First, it is useful because you don't need to compute waveforms. So if you have an adaptive method, a method that goes from one point to another, to another, to another, you don't know where are all the points. You have to go to the waveform model again and again, and it's tiring. Okay? So you now have a pre-computed set of waveforms in this tensor. You could also have a pre-computer extrinsic parameter samples, put them here. And the computation is a dot product, tensor product, actually. So just the computation of the waveform in the past methods would have taken you a millisecond for the fastest waveform models. Okay? And here, using the dot product, I can generate a likelihood evaluation in 100 nanoseconds. Okay? And that's on a one core CPU. That's the cheapest part of the computation. Okay? So if you want to do it on a GPU, you probably, I don't know, it would be unmeasurable because in one clock it will give you the result. So the result, okay, so wait, so let's talk about this. So in terms of a sampling scheme, that's actually a worse sampling scheme. Why is that? So if you have an integration method and it's one-dimensional, the scaling is such that the precision is 1 over n, where n is the number of points. If it's two-dimensional, you now need n squared points, but the precision is still 1 over n. If it's 10-dimensional, okay, for precision of 1 over n, you will spend n to the power 10 points. Okay, that's bad. Monte Carlo integration, the scaling is always 1 over root n. The number of points you're using, 1 over root n is the precision of the integral. So this is a stupid method. It's stupid to have a grid. But the reason that we can do that with a grid is that there are so many orders of magnitude in the likelihood computation that it just compensates on the fact that it's a stupid scheme. Okay? So we are talking about 1 core minute, I think, in the worst case. So the actual flow chart is a bit more complicated and more involved. So you draw some intrinsic samples and you save them to files. So this is just preparation once in your life. And something that happens is that you also have a trigger. Okay, so you have this incoherent triggering. Remember all these modes and precessing and eccentricity and all of these things. So after that, you pre-select the parts of the intrinsic waveforms that are relevant. So if the trigger has a chirp mass of 15 solar mass, you don't need the template that is 1.5 solar mass. It's irrelevant. Okay, so you prefetch whatever you need. You take a few of those and you figure out what are the external parameters that are relevant. So if you know that the time delay is exactly 0 millisecond, that means that if those are the two detectors, it comes from that ring. You don't need to evaluate that thing. That's a 10 millisecond delay. It's not in the game. Okay. And after you have selected the intrinsic and extrinsic parameters, then you just compute with the remaining tensors all the likelihood points, and you get the output. Okay, fantastic. Is it solved? I would say that it's a good fraction of the world solved. It still doesn't have all the physics, as in no eccentricity. Okay, so some students gonna have to add that. I don't know if my student, maybe you. But in terms of runtime, that's what we are talking about, core minutes, and this is the likelihood precision. So it's actually an integral. I can guarantee you what is the precision of the evidence integral. That's crucial for research. Okay, and half is what you need for research. Okay, so that's 1 chi-square point. So that translates to a loss in volume of, I think, 5%. Okay, which is smaller than the losses in, I don't know, PSD estimation. Okay. Now, minutes is a weird unit, so just tell me how many flops. Okay, so the pre-selection takes all the flops, and 10 to the 11 flops is something that your GPU should do in, I don't know, much less than a second. So if when push comes to shove, if the national security of the US depends on this, you should be able to do it in no time. What are the applications of this? So precessing search, we will have the triggering part of this pipeline. I hope soon. It's led, I think, by the group of Jay. So Jay now is a faculty at Johns Hopkins. And eccentricity search, I think that needs some work. So arranging the template bank in such a way that eccentricity could be added still needs a work. What about lensing search? So currently, there's this conundrum in which if you want to ask if two events come from the same intrinsic event, you're just viewing it through two different lines of sight due to gravitational lensing. Then you have to take this event and two events, and you have to ask yourself, are they consistent with the same waveform? Now, what does it even mean? It's like a 15-dimensional space. What does it even mean? The meaning of this is that you have to compute some evidence integral, and you will have even more parameters now in this evidence integral, and you will have to compare the joint search with the individual search. And you'll have to do that n squared times, where n is the number of events that are roughly the same mass. But if you have evaluated the intrinsic parameters and the extrinsic parameters on a grid, that n squared becomes n. Okay, so you can just do it. It's literally grid times grid sum. Okay, and that you could also make a non-catalog search of lensing. And is it you? If you want, it's yours. Multi-messenger search also, if you want to, if you know where is the GRB and you want to like integrate only that part of the sky, then .pe is the thing you want. Okay. But I don't know if you got the feeling, I certainly got the feeling that we are scratching the barrel, the bottom of the barrel. This is not the way to go. This is not the way to get tenured. And so can we go for a larger gold mine? And we said, okay, so multi-messenger astronomy has two sides. It has the gravitational wave side. It has the other side, the EM side. EM side is both optical / UV, as in the kilonova. And you have fantastic kilonova searchers here in Caltech. I can't compete with them. But you also have the GRB side. What about the GRB side? So I was looking at this thing. And here is a plot. It's a plot from Blackburn 2015. And I had the same deja vu from looking on the LIGO plots. So somebody is proud of this plot. And in this plot, what they say is, hey, my algorithm, so their algorithm, so you see these different weird things. So different detectors of the GRB. So the best detector in space of GRBs is GBM, the gamma ray burst monitor on top of the Fermi satellite. And it has like 14 different detectors, okay? And each of them points in a different place. So here they are projected on the sky. And what they try to do is to say, if I have a trigger from 2 detectors, okay, it means maybe I have a physical GRB and not some cosmic ray hitting 1 detector. Okay, it makes sense. And they said, okay, so what I want is to tune the detector of the second. So the second detector has to trigger. So there's the bright one, that doesn't count. The second one, if it passes this 4.5 sigma, then you say, I have a trigger. Okay, but then you ask, so if you do matched filtering, if you read the book of how LIGO detection works, there's matched filtering, there are formulas, there are proofs. Match filtering, there's a coherent SNR. The coherent SNR is like 12. I know, coherent SNR of 12. There's like a factor of 2 to shave off. Okay, let's begin. Let's begin. So first of all, why am I doing it? Science. So GRB, I don't know what's the parameter that determines if you detect a GRB, but my limited understanding is that the GRB is pointed and the gravitational wave is not. And how does a GRB die? So one way is to get too distant. That actually doesn't work because the universe ends before you stop seeing the GRB. Okay, so what's the other way? The other way is to get off axis. Okay, so if you get off axis, so I don't know. I tried to play as if I know some physics, and I tried to understand, it has to be a polynomial decline, and I computed the polynomial, and then I was explained that I'm stupid. Anyway, so if you have a more sensitive search, you will extend the angle, okay? And if you have a more sensitive gravitational wave search, you will extend the distance. So if you just search the joint catalog, you will be limited to this small triangle. But if you work your best to improve the gravitational waves and improve the GRBs, you might actually end up with something that has a much larger area. Okay, let's go. Let's do it. 3 years later, Ariel, this talented person, see what's going on with me? So Ariel, this talented person, has written a full pipeline. I don't expect you to read this. If you want to, like an approximation, it's the LIGO pipeline. Just watch the lecture from 5 years ago. It's the same thing with one change, which is nothing is Gaussian in this detector. It's all Poisson. So what does it mean? It means that you have a detector, and this detector is a photon counter. And the photon counting of LIGO counts photons in the, I don't know, 10 to the 15 or something. And my photon counter actually counts zeros most of the time. So the GBM most of the time counts zeros. If you integrate for a second, you count few. Okay, and comes a GRB that lasts 40 milliseconds. GRB, we are talking about few photons over there, few photons over here, and you need to figure out how to do these statistics correctly. So Ariel figured it out, and the hardest part was this thing, that the background is changing with time, and you need to figure out how to track it, and you need to figure out what to do with the misestimation of the background. A long appendix, it's there, okay? I will explain one thing, but that one thing is going to be in the end of this lecture, okay? So I'm glossing over things that are, I don't feel that they are very inspirational. So the search for the GRBs, the results are, thank you, Sterl, for the for the heads up. So more than 50% more short GRBs, and those are the ones that are certain, okay? And here is the, so not all of those are GRBs. I'll say later what am I plotting here. Each point is an event, okay? This is the peak energy. Usually something is called a GRB only if it has a peak energy that is high enough. So all these colorful things are all coming from all over. What is here? Galactic center, yes, there's a particular, in 2014, there was a particular source roughly to the direction of the galactic center that was emitting all these bursts, thousands. Okay, so if you take only the GRBs, then indeed it's coming from all directions, and we have a well-defined search. And then comes this point. Who ordered that? So now I have a headache. The headache is that apart from the GRBs, which I set out to find, I found thousands of these things, let's call them SGR flares. I actually don't know if they are all physically SGR flares, okay? And I found this thing, which is even larger family of some of them are X-ray bursts, some of them are SGR flares. I don't know what they are, okay? And somehow there's a gap, and I believe at least Elias didn't know. Didn't know what is this gap, okay? But it seems very interesting. And there's a few blue points. So what is this color? So when I detect something with this GRB satellite, there's always a danger that this thing is coming from the Earth. And the Earth, to our limited imagination, should not emit gamma rays. But actually the Earth, if you have a little bit more imagination, then it actually does emit gamma rays because there are lightning, and lightning somehow create things that in the end of very complicated physics makes gamma rays. So green, definitely the Earth. Blue, definitely not the Earth. Red, I don't know. Now here there are many things that are green and many things I don't know. So first of all, why do I don't know? If the energy is hard enough, and terrestrial gamma ray flashes are very high and very hard bursts, if the energy is hard enough, then the detector doesn't know. It doesn't matter at this point where is it coming from. The sensitivity is all the same. It becomes all sky. Okay, so you have many things that you don't know where they are. And a minute part of them are actually blue. So there are a few things here that are not coming from the Earth. And we could actually verify, there are lightning monitors. We could actually verify for at least one of them that it is not lightning. There was no lightning, nothing. So I don't know what is this very short GRB. Elias, maybe you know, I don't know. Who ordered that number 2? So we set up to find coincidence with gravitational waves. And I ordered that, but not that. Okay, so 20 seconds before an NSBH, that NSBH, 1912-19, there was a GRB. That's the localization of this GRB. And it's not from the Earth. There's no lightning as well. The duration is 40 milliseconds, which is, again, incompatible with a TGF. And the coincidence is 1 in 10,000 for this event. And there are like 10 events that you could consider that maybe they are involving some GRB, okay? I don't actually know how to get to 10, maybe it's 5, okay? So 1 in 1,000, I don't know what to do with it. I would have wanted that it would be better, that it would be from the other side and we would be 1 second and I'd be singing here, jumping and saying I found it. I don't know. So what are we doing now with this? We are going to every single gamma ray satellite that was operating in 2019, and we are begging for data. We are still missing AstroSat and Agile, but the other ones either should not have seen or did not see because they have reduced sensitivity from GBM. No luck. Okay, but let's change gears. Okay, so we searched for GRBs and we ordered and we got what we ordered. It's our punishment now. there's a ultrasat satellite. I should say that it's a real thing. This thing is going to fly in 2 years. And this ultrasat satellite, they made a choice, and the choice was to make it undersampled. They wanted very large field of view, and undersampling is something that happens when your pixel is larger than your point spread function. So here are pixels, and here is a point spread function. So a point in the sky sheds the photons in this area, okay? And this area is a subpart of the pixel. Now, what's the problem with it? What's the problem with it? There's a pixel. It will measure how many photons arrive. The problem is that if I have different images and I want to move them, I want to register them one in front of the other, I cannot move by half a pixel because I don't know if the registered 100 photons that were in this pixel, I don't know if this is the case or this is the case. Because if I shift by half a pixel, this guy moves 100 photons over here. And if it was that guy, then it doesn't move. It seems like a minute problem, but actually when you have millions of pixels and you try to shift and you subtract, you will get junk. You will get lots and lots and lots of junk. You will be able to realize that something is new only if previously there was 0 and now there are 1,000, okay? But if previously there were 100 and now there are 130, oh, forget about it. It's just a mistake, okay? So this is some algebra problem. So the rules of the game is that you get to see many of these images, many undersampled images. So you make a survey of the sky, make a survey of the sky. Oh, LIGO says there's a trigger. LIGO says there's a trigger. Where? There. I need to very fast slew. I will be in an orientation I've never seen this place before. And now I have to say now I have to say, is there something new or not? Okay, that's the game. And the algebra, I think, did not exist before. And Matan solved most of the problem, and Yair solved the rest. Yair is actually a professional programmer and also an Emmy Prize winner. You can ask later why. And after we solved this problem, we then looked, wait, is it relevant in other places? ZTF. In my PhD, nobody told me that most of the insanities you see, most of the things that are not real are coming from the times in which the seeing is best. Nobody told me. I would have immediately guessed that it's undersampling, but I didn't know. Not only ZTF, LSST, HST, JWST, Euclid, Roman, planned, SphereX. Undersampling is common for every wide field image because every single scientist will make the same trade-off. I want more area, and I'll deal with the algebra later. Okay? So it turns out that this thing is relevant everywhere. And Yair is now writing this in a way that a professional programmer writes it, and we will release this very soon. Very soon, as in the money to hire such a professional will run out very soon. So we have to put it out. Okay. And now let's explain one thing. Continuous pulsar detection problem. I said gravitational wave about this lecture. And actually, this is also continuous pulsar. Who says it's radio? Okay, so in gravitational waves, we are also looking for rotating neutron stars. It's the same thing. And radio detection of a pulsar and gravitational wave detection of a neutron star that is rotating, it's basically the same problem. So what is the problem statement? So let's begin with the pulsar, because that's, I don't know, refreshing. So if you have this rotating thing, and it is, I don't know, in orbit around the black hole, let's make it fun. So this thing is rotating hundreds of times per second, and the scale of this, unfortunately, is light seconds. Okay, so that means that in order to phase the pulsar, you have to correct for the orbit first. But I don't know the orbit. I don't know the orbit. How will I correct for it? And a Nobel Prize had already been given on finding pulsars that are in a relativistic orbit around a white dwarf. Okay, so this is definitely still an important problem. And there are targets, of course. You could say search for radio pulsars in galactic surveys and in globular clusters. So we have some partnership with the Max Planck Institute in Bonn on searching for globular cluster data of MeerKAT. And we have some collaboration with the group of Tom for basically the same thing, but different telescopes. So you could search for pulsars around the supermassive black hole in the galactic center. That's something that you really want. And you can search for continuous gravitational waves. Same lady, different dress. And also, you could search for Scorpius X1. So physics aside, the system that we expect most to emit gravitational waves as a rotating neutron star is Scorpius X1 because it is accreting the most and giving us the highest X-ray flux. And if there is some connection between the angular momentum it accretes and the angular momentum it emits due to gravitational wave, then this thing has to be the brightest source. And in fact, allegedly, if there's a balance of angular momentum, this thing in 04, I think, will just cross the point where you could detect it if you coherently add all the data. So this is very important. Okay, here everybody knows what to compute, but how to compute? That's the question. So here comes a family of algorithms that are called dynamic programming. Okay, so this is the Cooley and Taki FFT algorithm. You have some input array, it's one-dimensional. You take the even part, you take the odd part, you use somebody else's code for fast Fourier transform, and then you combine. Okay, and the reason why it works is that the formula for combining is so simple. Okay, you literally take this result of the even part, and you take the result of the you take the result of the odd part and you take the result of the even part and you add them with a twiddle factor. Okay, so you multiply by a complex number and that's it. Your algorithm is done. There's no reason why it should be more than a few lines in Python. And dynamic programming had already been used in pulsar astronomy. So fast folding analysis, Stalin 58, 3D dispersion, Taylor 74. I myself did something for detecting FRBs. And for extending to a better test statistic. And instead of an n squared, you get an n log n complexity. So this is whatever you are doing with your phone or any communication system now, if we didn't know how to do this in n log n, if we kept doing that in n squared, that just wouldn't work. Okay, so we all should be thankful for Cooley and Taki. Now, coming back to our problem, this is an impossible thing. Why? So if we take even hours of observing this system in a binary, okay, so let's say one orbital period, we will have 10 to the 9 options for the period. We'll have 10 to the 3 options for the dispersion measure if it's a radio cert. And then we realize this thing. We realize that the size of the system compared to the precision, so the size in light seconds, compared to, so this is like a time, okay? So that time, few light seconds divided by few milliseconds, it's like 10 to the 3, 10 to the 4, depending on what you think about this pulsar. And the number of possible orbits is this number to the power 5, okay? So 10 to the 20. Uh-oh, what will we do? So the existing algorithms close their eyes and say, okay. The entire orbit, just forget about it. Don't talk about this. Just make an FFT, and it will work for short enough piece of data. This was for some time what they wanted. And then Shri came along and said, no. We know better. We can do some acceleration search, and it will last for much longer. Okay. So from here to here, there's like almost 10 times more data. You will be more sensitive. Okay? Very, very, very lately, people began to do jerk searches that give you a little bit more data, but the scaling, t to the power 6. So let's do this. Fast folding analysis and log n. This is how it looks like. You have something and you have a jumping frog. And what you want is to compute all the integrals of the jumping frog, so all the integrals of these periodic crosses of this thing. So you begin by writing that one on top of the other. And then you realize, wait, a straight line, if I look only here, it's just either this or that. Okay, so there are only two options. And if I have something of length 4, it's either this or that or that or that. Okay, so it's only 4 options. So the number of options is proportional to t. Okay, but the number of segments is inversely proportional to t. So the volume is conserved. Algebra, algebra, algebra in the end. Just like Cooley and Taki is based on one formula, there's one linear formula for this guy. Okay. I can give you the presentation if you want. It's already published several times in several different languages. Computer scientists discovered this algorithm in the 90s. So pulsar astronomers already forgot it by the time that the computer scientists have discovered it. Fast acceleration folding, the same thing, the same lady, different dress. There's a one-liner that describes how to take an accelerating jumping frog and say, okay, in the left, I've computed all the integrals of accelerating jumping frog. On the right, I've computed all the integrals of accelerating jumping frog. So let's just join them by figuring out that the jumping frog I want, where was it on the left, where was it on the right? Here, there's no log n. The reason is that when you join segments, you actually go t cubed. So it turns out that it's just the largest part, just the last step that dominates the entire computation. Okay. And while I figured it out 10 years ago, Kendrick just published it. I should have published then and not smeared it for 10 more years. So here comes a trick. Wait, Barak, in the last step, you spend all the computation? Are you crazy? In the last step, you are looking for something that is SNR9. You already know if the sum of two numbers can end up 9 before you look at them. If there's nothing above 4, just move on with life. Don't bother looking at the other place. Okay? So that would save me a factor of 4. Factor of 4 less computation with a trick that simple? No, do it again. Okay, let's do it again. Okay, it's a factor of 16. Now I don't know, the threshold changed. Factor of 16, that easy? No, you have to do it again. Okay, and it saves a factor of 64. And then you realize, wait a minute. This algorithm looks very different. Okay, so let's evaluate it from the start. We have a process. This process is integrating. And while integrating, we are looking at the result and we try to figure out, is it good or is it bad? Now, we don't have enough information for positive identification. So the right option will come up from the blue distribution. The bad options will come from the red distribution. But there's going to be like 10 to the 9 red options for every one blue option. Okay? So if something is here, it's not coming from the blue distribution. It's still much more probable to come from the red distribution. But if something is here, it's not coming from the blue distribution. Toss it away. It's not relevant. Okay, so you can eliminate. So how does, now we need to go on the board and draw something. Draw a circle. I was told that if you want to think, draw a circle. So you draw a circle, those are all the options. And then you see which of them are relevant. And each option that is relevant, you continue the integration. You have several options of how to continue the integration. And at each step, you see what's relevant, what's irrelevant. Okay? So this is called pruning. You cut the branches There are two processes, expansion and elimination. Who wins? Elimination. This is obvious. Why? Because in the end, you are looking for the right solution. Allegedly, there is the right solution. There is one option that is statistically significant. You are looking for one. Okay, so in the end, elimination must win. Is it possible for it to win? Elimination, okay, is so SNR is root T. Elimination is e to the minus SNR squared over 2. So e to the minus T over T naught. The expansion is polynomial. So that depends on where the peak is. So if the peak is at T to the power 6, it would look like that. And if the peak is at T to the power 10, it would move a little bit to the side. Okay? So this is the volume as a function of time. And this is the total complexity, the complexity to reach the point of SNR root 2 times some k plus 1 factorial, where k is the degree of T. Actually, it's k factorial. I don't know why I have this bug. Okay. So you have, Barak, you have a process. It has all these steps. It gets wide. How do you tune the thing? How do you make sure that this thing actually converges to the right solution? Because you have so many different options to toss out the one solution to the trash, and nobody's there. There's no police. Nobody's there to tell you are wrong. Okay? So what do we do? So first, we say, okay, I have a threshold scheme, and I started here. If I tossed the right option, where did I toss it? I toss it where it is challenging. I tossed it here. I did not toss it over here. Here I can be very conservative. It doesn't matter. Okay? So now I also have a few trials. I have a few trials. I can try here. I can try here. I can try here. I can try here. So the name of the game is not the complexity of one process, it's the complexity divided by the probability of recovery. Okay? Because the number of trials is inverse to the probability of recovery. So now I know what to optimize. And I don't know how to select this. I don't know. Whenever I try to guess something, it was wrong. So we devised an algorithm. The algorithm is to find the optimal path in the threshold versus probability phase space. And after you find the optimal path, you realize that you have saved a few orders of magnitude as well. And the naive computation that was here, actually, we achieve exactly this. I think this is a result of some information theory thing that I'm not smart enough to derive. So the continuous gravitational search, the official LVK analysis is fantastic. Okay, so they have a very long coherence time that leads to the fact that they can almost utilize the sensitivity of the detector. So they leave only a factor of 5 on the floor. That's actually super challenging. The AEI search left only a factor of 3 on the floor by using the biggest computer on the earth. Okay, so can we do it? If I compute what's the complexity, it's 10 to the 16. You remember what is 10 to the 16? So a teraflop is 10 to the 12. And our GPU is 10 to the 15. So it's like a day of a GPU. So Barak, where are the results? We're still dealing with the statistics. So stay tuned. Okay, we don't want to drop a factor of 3 in the statistics. It would be idiotic. Okay, so I told you about the work of these people. Pravir is looking for a place. If you know what you're doing, hire Pravir. And I'm hiring. So thank you.
Okay, questions for Barak from any of the many topics? Sure.
Well, it's just a comment. Sometimes you don't actually have small pixels, even if you had for reasons of practicality. So in ZTF, the for the 16 CCDs, we had a choice. The total area is fixed, 15 micron pitch or 9 micron pitch. And we chose 15 because 15 over 9 squared would be the amount of disk storage, data bandwidth transmission, and computing. And my view on that is projects which fail tend to overdo things. It's much better to do something than something which is ideal and sort of gets not done very well. And the assumption here is that was made, I don't know, 10 years ago, is there'll always be some bright person who'll come and figure out the last fit.
Okay.
Other question?
Thank you for the nice talk. The very fast, the .PE is very appealing. I mean, if PE can
Yes.
really be done in, minutes instead of
Yes.
hours, that's a big deal.
So I should correct myself. The evidence integral is in minutes. That's what I cared. Usually we think of the evidence integral as harder than PE, but in integration method, actually it's easier than PE. The PE is about a factor of 20 to 40 times slower, but it's still minutes on a server.
I see. I mean, I guess my question is, are the algorithms mature? Are they available? That sort of thing. It sounds like a very useful tool.
Available, it's on GitHub. Mature, I'm trying to get them to grow up by getting Jonathan to do PE for all the O4 LIGO events, make sure that whatever he throws at that, it works. It will get there. It will get much more mature with involvement from people who actually do PE for their life in the collaboration. I welcome you to contact us because I think there's no huge barrier to jump. It's just now getting all the waveform models to have a bank and to get each one of them to have all the harmonics listed and sampled on that frequency. It's a work to do. You want that mature and you want that for you. Talk to us. Okay, we can't guess what you want.
So in doing this parameter estimation, I'm kind of curious. One of the issues that I wonder about is that in all of the different estimation problems, we don't know, there's kind of a figure of merit of how, what the SNR of the event that you would see would actually give you some sort of actually informative posterior. Just wondering if the techniques that you have could be used to help us to develop science cases by telling us what all those thresholds are on every form of parameter estimation that we might choose to do.
That's a use case. I welcome you to interact with us.
Open question.
So I was curious about your innovation and dealing with undersampled images.
Yes.
So
I know I promised it 2 years ago, and
so
I know what happened. A war happened, and the student kind of had to finish, and we did not put out the paper and the code. But this has to happen for Ultrasat, and it will happen this year.
awesome. But the question I had is, how does it compare to algorithmically? How does it compare to Drizzle? Because currently, what people do to deal with undersampled images is dither, and then just have the light leak out to different neighbors when it lands at different portions of the pixel.
Yes.
So how does I think describe the algorithm, right, in terms of.
So Drizzle is the part where if you control the telescope well enough, you could move half a pixel sample, move half a pixel sample, move half a pixel sample, and you can just then interleave the images. It turns out that this is the correct solution when you can really point to the sub-pixel accuracy. And one of the ways we check the code is that you output the same as Drizzle when inputted with something that is as structured. But it will also catch the situation in which this image is like that image is like that, this image is shifted, that image. So
Rotation.
So it's a generalization of Drizzle, I would say. Okay.
again, thinking about those weird sources, that plot you had with the peak energy and time distribution.
We discussed so many things. How did we not discuss this?
Yeah.
Yes.
That's because we still have lunch tomorrow. Okay.
You can rejoin dinner at 3.
Soft gamma repeaters are actually common. The bright bursts are once in 10 years in a galaxy like ours. And there have been a few seen from nearby galaxies, I'm saying over the last 30, 40 years. Okay. So the soft gamma burst threshold, if you plot them in supergalactic coordinates, I would predict you'd see it along the equator of the supergalactic plane. So that would be a firm physical evidence of what was.
So they are, I didn't show this, but they are forming on the plane. You could show the plane of the galaxy with.
So you're saying they're on the galactic plane,
With-
you're saying supergalactic,
What does it mean, supergalactic?
the local group. Basically,
No,
the nearby galaxies.
You could get bursts from our own galaxy, other things, but I'm not sure. I mean, some stars, actually, active stars have, I don't know much, but maybe they, many active stars certainly have hard extension now, whether they're going to the soft gamma, you have to not, let's see, what is it, -1, no, 10 keV, okay, it's possible, maybe 30 keV, it's possible. I'm talking of soft gamma ray repeaters, okay, which are different. And they, you should be able to see from other galaxies, because we've seen them, but I think we only see the very brightest one, the 1 in 10 year, it's been seen from, I think maybe one from Andromeda and so on. So it'll be useful to actually test the supergalactic hypothesis. And maybe 15 years ago or something, I remember a paper where someone actually tried to do this. I think Tanvir et al. They claimed they were seeing an excess.
This is very interesting. We will definitely
And
try
this
to
was
understand.
exciting. And this soft gamma repeaters, now we know they're deeply connected to fast radio bursts. Not exactly the same thing, but let's say it's the same beast. Okay. And you should see the same effect in FRPs eventually.
Interesting. This is definitely something to try to do, and you're already the second person who asked me this week. Can I localize a few of those to the neighboring galaxies? So, and yes, that's on the list of what to do, but it's not obvious that we will be able to do it because in the end, GBM localization is not best. This instrument is.
That's the reason I didn't say localization. You really want to just look at some photo.
But a third of the sources, roughly, we either find the counterpart in Fermi, not in Fermi, in Swift, and a few you can find something in integral, and a few you can find some. And so, there is still hope, even in hindsight, to find better localization. So if something is happening a lot, then we could probably pinpoint where it is. It's not hopeless, but we are still trying to figure out what of this thing to do because we can't do everything. So.
How many of these are from the same source in terms of just flares from the?
I don't know.
source? Like,
Fair answer, I don't know.
connect the dots, right, in terms of-
Many times you see, okay, so we did a plot of time versus where does it, like projection to the galactic plane. And it seems that there are at least 10 different sources in the thing. And many times you see that in a few months, suddenly you have this thing shooting at you. So I did not do a thorough counting, and to be frank, I'm not sure that it's easy. So you are welcome if you are interested to interact.
Okay, I think there's cookies below. There is one slot.
Wine and cheese.
Wine and cheese, sorry. There is one slot available for dinner. We had a cancellation.